Okay, so welcome to the second lecture of Statistical Thermodynamics for Engineers. So in this particular lecture, we are going to cover the principles of probability and statistics. So let's look at it. Things will be probability and statistics. Okay, so let's take a situation given, say, NS mutually exclusive, equally likely points in sample space with any of these points corresponding to a random event A. So given that there is NS mutually exclusive, equally likely points in a sample space with any of these points corresponding to a random event A. So let's take an example so that you can understand it the best. Let's take a deck of cards. So deck of cards, okay? So where NS is basically 52. In a deck of cards, there are 52 cards, as we know, right? Now, the probability, therefore, if we want to know the probability of drawing an ace from a well-mixed card, deck is given as PA, where PA is equal to 4 by 52 or 1 by 13. So here A basically designates the random event, of an ace. So this should be now understandable that the probability of drawing an ace from a well-mixed deck of cards is given as that random event is called A. Now, if we consider two random events, so now let us consider two random events, A and B. These are the two random events, A and B, in the same sample space. Right? Two random events in the same sample space. Okay, let's look at that. Now, if that is the case, then if A and B occur in the same sample space, then probability of A plus B, okay, is probability of A plus probability of B, because A and B are mutually exclusive. So physically this means, this probability of A plus B means that A or B or both. This is what it means, right? So physically this is what means, that A or B or both. Okay, so example. We can take an example right now. So say this is an example. Okay. So let's say the probability of picking a king, say that K, or a queen Q, okay, from a single deck of cards. Let's calculate this now. So this will be P K plus Q. Okay, is probability of getting a king plus the probability of getting a queen, which means it is 1 by 13 plus 1 by 13, which is basically 2 by 13. Okay. So probability of A plus B is more like a union B. It's like a union. Okay. Now let us take this same example and take it a little bit forward, and we take this same example and say the probability of picking a king, which is K, from one deck, okay, and a queen, which is Q, from a different deck, right? Okay, so these are now two different packs of cards that we are talking about, right? So they are not from the same deck, they are from two different decks. So in that case, we write probability of KQ is more like multiplicative, 1 into 13 by 1 into 13. Because in this case, these are two different sample spaces. Okay, so these are two different sample spaces, right? So in this case, your P A B is more like P A into P B. Okay. So this essentially implies that these are two mutually independent events, in two different sample spaces. Okay. So when we talk about PA plus B plus C, it means PA plus PB plus PC. Okay. These are what we call mutually exclusive events. These are mutually exclusive in nature. Okay. And when we say P, A, B, C, these are PA, PB, and PC. These are mutually independent. Okay. So these are mutually exclusive, and then they are mutually events. Okay. So now let us look at some of the permutation and the combinations in this particular case. Okay. So this is like rehash of statistics that we are doing. So permutations and combinations now. So let's look at those now. Okay. Now let us consider an urn. Okay, which contains say 4 marbles. and which are marked as A, B, C, and D, right? So this is an urn, okay, which consists of 4 marbles. Okay, so these are 4 marbles, and they are distinguishable marbles. They are distinguishable marbles. So our aim is to randomly select marbles from the urn without replacement. So what is our aim? Our aim is to randomly select marbles from the urn without replacement. Okay. So naturally, when you do something like that, what you see that, okay, so the first marble, okay, obviously you can have 4 possibilities, right? 4 possibilities. Okay, so first marble, you have 4 possibilities. The second marble, once you pick it up, it has got 3 possibilities, because we are not replacing the marbles, and then the third one has 2, the fourth one has only 1. So these are what we call 4 sequential but independent choices. 4 sequential but independent choices, right? But they are sequential in nature. So this can be written as 4. The first one can be drawn in the case of 4. The next one is 3. Third one is 2, and then 1, which gives rise to 24. Okay? So there are 24 possible ways, okay, of randomly okay, selecting marbles that are distinguishable. Marbles. Now, if these marbles were indistinguishable, if these marbles are indistinguishable, guess how many ways they can be ranged, or they can be taken out, right? So there is only, from 24 just goes to 1. Okay, there is only one way. Okay, only one way, because these marbles are now indistinguishable in nature. So we generalize. Now what we can do is that we can generalize this. Okay? Our hope is to generalize. We generalize this. Okay? So it is like we choose m items, okay, from a sample of n objects without replacement. Right? Without replacement. So, permutations, if we write P as a permutation of n objects, m items taken out, right? So these are permutations. This is given as then n. First you take out n, and n minus 1, n minus m plus 1. Okay. Now this can be written in a formal way of n factorial divided by n minus m factorial, right? Whereas of course your m is less than n. So this is the criteria. Now if m is equal to n, right, then p n comma m becomes nothing but n factorial, which is exactly what we saw here. To look at it, so this is basically 4 factorial because there are 4, right? So this is n factorial, okay, where if you recall 0 factorial is 1, just to keep this in mind. So you can understand, so this is very simple. So instead of 4 objects, now we have n objects, and you are taking out m items of them. You can take all the n objects. In that case, m and n are the same. Now in comparison, the number of combinations represents all the different subsets containing m items that can be sampled, from n distinct objects. Okay. So either the particular arrangements of m, but a particular arrangement of m, but it should be remembered here, to look at it carefully, of any particular arrangement of m, okay, m objects within a subset, okay, is irrelevant. Okay. So basically, if you write it as C n comma m, this is n factorial divided by n minus m factorial divided by m factorial. It's n arrangements you are not taking into consideration here. And if n is equal to m, then C n comma m becomes equal to 1, which is exactly what we saw in the last one, that when we have 4 objects which are basically indistinguishable, and you are taking all 4 of them out one at a time, there's only one way that you can do it, and so therefore this is what it is, right? So this is a more generalized representation of what will happen when you actually have this. Okay, so this brings to that you have now can see what a permutation and a combination actually kind of looks like. Okay, in this particular case. So now let's take a step back and let's look at some few other things, which is called the probability distributions now. So probability distributions. The rest of the things you can self-study from the book. So probability distributions is like basically if you have this kind of a chart, say for example, let's look at it. So this is like, for example, the test scores, right? So test scores in a particular exam. So this is 40, 50, have like this kind of thing. Starts to form from here, something like this. Okay. So, and this is the fraction of the students. Fraction of students. Okay. So this is like the total. This is like, you know, you can have 0.1, 0.2, 0.3, etc. Right? So this is what we call a discrete probability distribution. This is called a discrete probability distribution. Discrete probability distribution means that when you actually now sum the probability of the individual scores, it goes from I is equal to 1, where xi is basically each grade. Right? So when you write x bar, which is basically nothing but this is how I write. This is called Dirac notation. Dirac notation. Okay. So this is nothing but summation xi and dxi, which is basically each grade multiplied by its corresponding frequency, in this case the probability. Okay. So similarly, you can get something what we call the variance, which is sigma square. Some of these are known to you, so it is like xi minus x bar square, and then the average of that. Okay. So this can be also written as xi square bar minus x bar square, and a subset of that, which is called the standard deviation, essentially, is x square. And so this is basically now this entire thing, xi square bar minus x bar square, and then you take the whole root of that. Okay. So this is basically what we call the standard deviation, and that was the variance. Standard deviation, right? So if you have to consider the variance, okay, that is basically xi square bar. This is just the individual terms. So xi square into the corresponding pxi, which is nothing but the weightage. It's like if you have done, weighted. So each score has got a particular distribution. So this is exactly how you compute it. So this is the percentage. So in this case, that is the probability. Okay. So if you consider the case that now, if you consider a case in which a more realistic distribution, okay, so in this realistic distribution, where the number of students, in this case it was rather small, distribution of students is large, very large, right? So therefore, the discrete probability distribution in that case, discrete probability distribution in that case approaches, okay, what we call a continuous one. Which is also known as the probability density function. Fx. Okay. So of course the probability density function has to obey the fact that fx dx is equal to 1. Right. So this is integrated over all possible values of x. Right. So if you write it, if we just plot it, we just plot it, you'll find that this is fx. So this is something like a graph like this. So for example, this is x. So this is the graph fx, and let's mark a shaded region here for the convenience. So this is basically a small segment which is dx on this particular graph. So if I write dpx, okay, that will be fx into dx. So that is what it is, fx into dx. And the probable, and if I have these markers as, there is a point A, let's mark a point A, and then mark a point B in this graph. Okay? The probability of x greater than equal to A less than equal to B is given as integration from A to B fx dx. Okay? So this is the probability that x lies between A and B, which is basically this part of the graph. Okay, so that is what it is. Okay, so this is the probability of finding B among these two. Okay. So there is also something what we call the cumulative probability distribution. The cumulative probability distribution. Okay, so let's call that fx. Fx is nothing but from 0 to x. You integrate it, is the dummy variable. So and once you have p, a greater than equal to x less than equal to b, you can write it as fb minus fa. So that is the cumulative probability distribution. Now, there's a couple of things more to note. For any function of x, say hx, any function of x, average of hx is basically hx into fx dx. Okay, so this is like a, as we told earlier, it is a statistical weighing function for hx. Now, if hx is equal to x, then average of hx is equal to x bar, which has got the simple thing as the first moment, which is the mean. If hx is x minus x bar square, okay, then this gives you the variance. Therefore, the variance. So these are basically what we call statistical moments. Okay. So in the next class, we are going to look at some of the more distributions of such statistical moments, and we are going to look at some distributions like the binomial distributions, the Gaussian distribution, and the Poisson distribution before we move on to how these distributions are linked with statistical thermodynamics in the first place. So thank you so much.